Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper data structures. This is a module where we talk about red black trees. This is a special type of balanced binary search trees. We had already discussed in the previous modules about balanced binary search trees. There were three types of balanced binary search trees we are going to discuss. We already completed AVL trees. Now we are going to talk about another interesting balanced binary search trees called red black trees. So, this module, these are the people responsible for the development of these modules, and let us look at the learning objectives this module. So, first we are going to understand the concept of red black trees, then we are going to talk about the properties of red black trees, because this concept is a slightly different concept. So, we are talking about concept separately and properties separately. Again we are going to talk about rotation of in red black trees. So, here again we have the same thing. So, when we have an imbalance, we will try to do rotation to get a balance, that remains the same, but the way we do it is different in red black trees. So, we are going to describe that, and we are going to explain insertion into red black trees alone in this module. In the next module, we will be talking about deletion of red black trees, because that is completely different. Even in AVL trees it was different, here it is completely different. So, we are going to talk about that completely in a new module. And then these are the terms red black trees, rotation, and the red black property. So, these are things that we are going to discuss. So, let us start with what are red black trees. So, red black trees are a variation of binary search trees to ensure that the tree is balanced. This is similar definition that we had for AVL trees. So, what is the difference? We will come to that. Okay. So, height is of the order of log n, where n is the number of nodes, similar again to AVL trees, where we wanted the height to be of the order of log n. So, the operations if the height is log n, the operations will take of the order of log n time in the worst case. So, binary search tree, but here when we are representing the binary search tree, the binary search tree will be represented with 1 bit per node extra, and that will be the attribute color, and the color can be either red or black. Okay. And all other attributes of the binary search tree are inherited, that is, you will have a key, you will have a left, you will have a right, and you will have P, and all empty trees are colored black. Now, please note we are coming to the black properties, red black properties, specific properties. One is every node will be colored either red or black. So, it will have an attribute called color, and then all other attributes of BST trees or binary search trees are inherited. All empty trees or all empty trees, that is leaves, are colored black. We use a single set-in nil for all the leaves of red black trees T with color nil equal to black. So, we just specify that is it. And the roots parent is also a nil of T, that is normally we do not have a parent for it. Now, this red black properties, let us go. You have to understand this red black properties well in order to understand red black trees. So, the data structure requires an extra 1 bit color field in each node. So, as we have already discussed, every node is either red or black. Okay. Now, let us look at the properties. One is that the root is black. Okay. Then every leaf is also black. So, that means every real node will have 2 children, null children, and those null children will be black. Now, if a node is red, then its parent is black. If you cannot have a red child having a red parent, it can only have a black parent. If a node is red, then both the children are black. That means, you can note that the red node comes between 2 black nodes, its parent is black, both its children are also black. That means, we cannot have 2 consecutive reds in a path, on a path. That is the fourth property. Now, all simple paths from a node V to the leaf have the same number of black nodes. Now, this is that height balancing coming in. So, we have what is called a black height of a node X. I will repeat this again, we will go to the properties once again. So, all paths from any node X to the leaf will have the same number of black nodes in a tree, in a red black tree. This is called the black height of X. Okay. So, for all paths from if you take a node, all paths to the leaf should have the same number of black nodes, and that number of black nodes is called the black height of that particular node X. Okay. So, again let us repeat, root is black, leaf is black. Okay. So, that means you can even have null things and call it leaf and say it is. So, real node and then it will have to, you add to null and put it black. Then if a node is red, its parent is black. If a nodes both the children are black, that means the number of black nodes is 3, 7, 3 and 7, 3 and the null node. If you take the path 10, 7, 8, again you will not count 10. So, 7, 8 null, again 3, 7, 8 the other side of null 3, 7, 3 null through 5, again 3. So, that is the property that says same number of black nodes from every node. This is true for every node. Okay. We took 10 at the root node. So, this is the red black properties. Now, let us talk about a black height of a node. So, here you have a node, the number of if you take 50, the height is 1, the black height is also 1. Remember, the black height is the number of black nodes there are from the in the path. Now, if you take 47, you will not count that node. So, 50 is red. So, you have only one nil node. So, the black height is 1, but the height is 2. Now, if you take 41, you have 47 and nil as the two black nodes. So, you have black height is 2. If you take 27, you have 47 and nil only. So, the black height is 2. You understood what is black height? So, black height is number of black nodes from the node to the leaf excluding itself. Okay. So, if you take 26, you will see 17 and nil. So, 2, 17 and nil, and so and the black heights will be the same, all paths it will be the same, only then for a node you can put the black height. This is what we defined as black height of a node. So, height of a node is the number of edges in the longest path to the, that is the normal definition of height to the leaf. Black height of a node x, BH of x, is the number of black nodes, I am just repeating, including nil, on the path from x to the leaf excluding itself or not counting x. So, that is what we discussed. Now, when we are implementing the operations, we have access operation and update operation. Use the BST algorithms without any change for all those operations, simply ignore the color node colors. The worst case will be of the order of log n. So, that is what we do, and insert and delete, worst case is of the height is of the order of log n. We have to guarantee that the modified tree will still be a red black tree. So, these properties have to be maintained in an update operation. Other operations where you do not do any insertion deletion, nothing changes. So, operations for restructuring the tree after insertion and delete operations on red black tree, it is a local operation in the search tree that preserves the binary search tree property. First thing we have to ensure that you have to preserve the binary search property. So, rotations take a red black tree and a node within the tree, and together with some node recoloring, they help restore the red black tree property. So, what it takes a red black tree and a node within the tree, and together with the some node they do some recoloring, so that they help to restore the red black property. So, change some of the pointer structures also, but that at any cost you should not change the binary search tree property, that is taken for granted. You need to have the red tree properties also, but you should not change the binary search property. Now, there are two types of rotation, left rotation and right rotation. Okay. So, let us, rotations are the basic tree restructuring operations for almost all balanced search trees, binary search trees, balanced binary search tree, balanced not even non-binary search trees, everything. Rotations are what we do for tree structuring. We have seen that when we discussed ABL trees. Now, rotations takes a red black tree and a node and changes the pointers to change the local structure and will not violate the binary search property as we have seen. You have left rotation and right rotation, they are inverses of each other normally. Now, if you take this node, this we have not gone into left light, see. So, left rotate t about x, what you do is you left rotate means you have to go the other way. So, y becomes x and x becomes a child. Right rotate means you take right rotate means you take alpha and rotate it. So, you can have rotate about y. So, what you are doing is you are taking that and rotating it. So, this is y will go to x and so on. So, you have left rotate and right rotate, they are inverses of each other. Now, um, red black trees, let us take a right rotation. So, you have a right rotation about y, then what do you do? X about y, y is called the pivot. So, here you have to do a lot of pointer manipulation. So, x keeps its left child, but what happens? Y keeps its right child. Okay. Y keeps the right child. So, both are kept. So, it remains the same. So, x keeps its left child, y keeps its right child. X's right child becomes y's left child, okay, and x and y's parents they interchange. X previously y was the parent of x, now x is the parent of y. So, we have done what all? We have x keeps his left child, y keeps his right child, that is there. This is for right rotate, and then x's right child becomes y's left child, okay, that is b in this case, and x and y now become inverse of each other. Of course, not exactly in the same way as you see. This we have seen before in AVL also. Now, assumptions of a left rotation on node x, the right child of x is not nil, that is the assumption we make. So, idea pivots around the link from x to y and makes y the new root of the subtree, and x becomes y's left child, and x y's left child now becomes the x's right child. So, this is left rotation. This is the inverse of what we did for the, and here now let us look at left rotations of red black trees. Now, suppose I want to rotate left with 9 as pivot. Okay. So, what we have to do is when we do a rotation left with 9 as pivot, rotation left. So, we take 12, 12 becomes the parent and 9 becomes the left child of 12, and 11 which is 12's left child becomes 9's right child. So, that is what we have done here. This is the left rotation. Now, right rotations, assumptions for right rotation on a node x, the left child of y is not null, that is an assumption we make. Left child, right child, left child of y, okay, is not null, and the same pivots around the link from y to x, and makes x the new root of the subtree, makes y the right child, and x's left child beta becomes y's left child. So, this is the same thing that we did for left rotate. Now, the operation insertion and deletion cause modifications to the red black tree. In this module we are discussing only insertion. The operation itself, okay, that itself, the color changes and restructuring the links of the tree via rotations has to happen. So, the operations of insertion, what modifications they do? The operation itself is a modification, color changes is a modification, and restructuring also happens. So, changing colors, for example, if you had it like this, you will change it like this, or through rotation where we have already seen either it could be a left rotate or a right rotate. Now, let us look at insertion in a red black tree. So, the goal is left rotate, right rotate is similar to what we saw before. We have not spoken about the color yet, we will come to that. So, suppose we insert a new node z into a red black tree. The idea is insert node z into the tree as we do in an ordinary search tree, binary search tree, and color the node red. Restore the red black tree property. We do not know where z is inserted, we will come to that later. So, the idea is you find z, I mean insert z into the red black tree as you would do in a binary search tree, then color that node you have inserted as red, then you have to restore the red black properties. Remember red black properties, if you have a red node, its parent should not be red, its children should not be red, both have to be black, all those we have to do. So, let us see. So, let us look at this particular red black tree. So, now the first question, 35 is the node we have inserted. So, let us insert 35. So, we have inserted 35. Now, if we color it red, we are actually breaking property 4, it is violated, because if a node is red, then both its children are black, 38 is red, both its children are black, here its child becomes red. So, we have violated that property. If you put it as black, for example, if you insert 14, property 5 is violated, because in all other paths to the root the number of black nodes is 2, but here the number of black node becomes 3 when you insert 14. So, all paths from a node to its leaf has to contain the same number of black trees. So, the problem is what to color a node when you are doing an insertion. This is just the issue that we were speaking about. Okay. Now, insert. So, new pair is placed in a new node which is inserted into the red black tree. So, there are new nodes, color options is there. If it is a black node, one route to external node path has an extra black node. So, that is a problem. This is hard to remedy. If it is a red node, one route to external path may have two consecutive red nodes, okay. Then may be remedied by color flips or by a rotation. So, this is the basic color options that we have. Black, if it violates the black property, very difficult to remedy it, but if you violate this property, red node property, because of coloring it red, it is easy to, you have to do some color flips as well as you have to do some rotation. Now, how to fix the property 3, that is the property 3. Let us look at this. We are going to move the violation of property 3 up the tree. Idea only red, what is the property 3? Property 3 is a red node can have only a black parent or a red node has only 2 black children. So, only red black property 3 might be violated. Move the violation up the tree by recoloring until it can be fixed with rotations and recoloring. So, that is what you will do. We have to restructure the links of the tree via rotation. So, the problem with insertion is every node is either red or black, every leaf is black. If a node is red, both the children are, we know these properties, just stating it. If a node is red, both the children are black. Every path has to have the same number of black nodes and the root is always black. So, if you insert 8 here, where does it go? So, you insert 8. So, if you insert 8 here, it will normally go to as a left child of 9. Okay. Now, so it will go here. What color should it be is the next question. Okay. So, remember this does not violate the property because it is still its children are black, its parent is also black. Solution, so you have to recolor it and put some value. Let us see what to do. Can it be red? Cannot be red as per property 3, cannot be black as per property 4. So, what do we do? So, we have to, so here in this case, 1 minute, in this case there is no problem. Now, suppose you insert 11, you have 11 there. Now, the property is in, if you color it 11, what red, what will happen? That property 3 is violated. If you color it black, okay, what will happen? The number of the path property is violated, because 9 path only 1, but when you go from 9 to through 11 you have 2. So, property 4 is violated. So, we have the solution is to recolor the tree. So, let us take the case 1. Now, here we introduce a concept called uncle. Now, who is the uncle? My parents brother, or I mean sibling is an uncle. My parents sibling is an uncle. So, let us assume that Z's uncle, okay, you can see the Z node as B, Z's uncle is is Y. Now, Z is a right child, okay, Z is a right child. So, parent sibling. So, that is what we have. Y is the uncle of Z and Z is a right child. Now, the parent of Z, that is Z's grandparent, must be black. Here C is black, and Z and parent of Z, A and B, must both be red. Yes, it's this is where you have case 1. So, case 1 says that you have a node Z, okay, which you have inserted and you have colored it red. Okay. Now, Z's uncle Y should be red, yes. Parent of I mean the grandparent of Z should be black, yes. Z and parent of Z should be red, yes, okay, both are red. Then what should you do? Color P of Z, that is A, black, okay, that we have done. Then color Y black, that uncle, so that also we have done. And then color parent of Z, that is C as red, also we have done. Okay. now z is equal to parent of z. Now, the new z we change. So, this is what is happened when we have the case 1 fix up. Okay. So, I will just repeat it. You have some conditions you have to meet. One is z is a right child of wherever you are going from. Then the uncle is red, z's uncle is red, its grandparent is black, and z and its parent are both red. Then this is a case of case 1. What is the solution? You color the parent of z as black, okay. The sibling, I am sorry, the uncle also black, then change the color of the grandparent to red, and then make the grandparent a new z. This is the fix up for the case 1. Okay. So, push the red violation up the tree, that is what we have done. We have pushed the red violation which we had, because A and B together could not have been red. So, that we have pushed up the tree and we have satisfying the red black property. Some action whether z, the same action whether the left is z is a left or a right subtree, does not matter, it will be the same action. Now, before we go to case 2, let us go to case 3. Okay. So, now what you have here is z's uncle is black. Now, z is here left node. So, here but that is not a condition. So, you perform color changes and do a right rotation. Preserves property for all downward paths contain the same number of black nodes, that is what we are preserving here. Normally, there we colored it red, right, here we are coloring as z as red only. So, z's uncle y is black, so that we have z is a left child, yes, okay, and then there it was a right child, that is the two properties. Now, the idea is color the parent of z as black, so B is colored black, okay. The color the grandparent as red, which we have done, and do a right rotate of T with parent of z. So, rotate that. So, rotate B about C. So, if you rotate that, you get this thing and you have the balance tree. So, only in case 3 you do a rotate, there we did basically color change, here we do a rotate, here we do a right rotate. So, no longer 2 reds in a row and P of z as P of z is now black, and so everything is fine. Now, now we go to the case 2. Now, case 2 is z's uncle is black. So, z is the same. So, z's uncle is black, fine. Then z is a right child, same as before. Now, here the idea is, now z becomes the parent of z. So, that is the new z. So, now you interchange the two. So, you do a left rotate with the t and z, with respect to z you do that, and now z is a left child, okay. Now, z is a left child and both z and P of z are red. So, this becomes a case 3. So, what we have done here? Here you have z's uncle y is black, z is a right child, as you can see z is a right child. Now, what do we do? What is the solution we have? We make z the parent of z. So, now we call z as A, and now left rotate it about z, and then now z becomes a right child and both are red. So, we have not solved the problem, you have to go back to the case 3 where both are red. So, the same we have now we have got, as you can see, that is the case 3. So, now let us take an example and do this, we just did it with that. So, let us assume we want to insert 4. If you want to insert 4, what we have to do? We have inserted. Now, what happens? There are 2 consecutive red nodes, okay. So, z and P of z are both red and z's uncle y is red. So, this is a uncle y is red. So, this is case 1. So, in case 1 we do the what all has to be done. So, what all has to be in case 1? You remember what we did in case 1? We colored first we colored y as black, and then we colored the grandparent as red, and then we colored the parent as black. Okay. So, that is what we did, and so we did that and we get this new tree. Now, what happens is all the properties now z's uncle y is black in this case. Why do you want to do? Because we have 2 red nodes now consecutive. Now, you can see them moving up. So, we have done that, but what happens? 2 and 7 are both continues to be consecutive nodes red. So, now my new z is 7, okay, that is what we saw there also, new z is 7. Now, 7's uncle y is black. So, and z and p of z are both red, and z is a right child, and so this is boils down to case 2. So, what do we do? Z and p of z are both red, okay. So, case 2 both are, yeah. So, what have we done there? We do the operations that we had to do for case 2. So, Z you have to do a color change and you have to do a right rotate, which we have done, and we have got this as the result. You can see that Z and I mean 7 and 2 have been right rotated, and the Z I mean we have changed it to left child and so on, and we have changed the colors also. But again we have 2 consecutive reds. So, it goes back to those are 2 consecutive reds. So, and its uncle is black. So, we know which, and Z is a left child. So, those conditions we go to case 3. So, case 1 we have some conditions, case 2 we have condition, now we come to case 3. When we come to case 3, what happens? We have that case 3 condition where we take the thing, and now 2 is the Z, and we have to do a rotate and things like that, and we get the final tree this way. So, in this particular module, we have discussed the concept of red black trees. This is completely different from AVL trees. Actually, he is keeping the balance by ensuring that the colors are alternate, but basically property 4. Property 4 is the black height. So, he is maintaining the black height, it cannot change too much. Okay. So, the black height is very important, and that is how he is retaining the balance, if you have understood that. So, that is the concept of red black trees, and we discussed the properties of red black trees, and we described rotation of red black trees. We also explain insertion of red black trees. The deletion we just touched upon, the detailed deletion we will be doing in the next module. So, thank you.